Hello, I'm Shivan. Welcome to our presentation.
Welcome to our 123 presentation. I'm Emily.
Hello, I'm Alex.
Hello, it's Andy.
So first we're going to go over our compression and transmission pipeline, and then we will show a demo.
Okay, for motion detection, my implementation is to break the image into blocks and compare the block of the compression image to the block of the key image.
After motion vectors, we do a YCBCR color transformation. We subsample the chroma components more than the Y channel to compress while keeping good visual quality since we are less sensitive to change in quality to chroma components. We apply bilinear rescaling for the resampling, which additionally adds a low-pass filtering effect due to averaging.
After chroma subsampling the keyframes, we use the Haar wavelet transform to project each channel into a more sparse basis. Our implementation mimics the Pi wavelet library and uses filter banks for fast computation. The first thing we tried was choosing a base frame and subtracting that base frame from the rest of the frames. Then we used a wavelet transform on each of these differences. Another method we tried was block PCA. This method worked extremely well for GIFs where only a small segment of the image moves in time.
We applied uniform dead zone quantization, which is the same as regular with twice the step width for zeros. This optimizes our run length encoding for more compression. We decided to quantize each subband separately instead of all at once because of the differing dynamic ranges of each subband.
For run length encoding, I mapped the numbers into number frequency tuple. For Huffman coding, I generated a dictionary based on the frequency of numbers and then translated the unsent int into dynamic length bits.
In communication part of the final demo, we use a method of digital signal modulation called OFDM. When we get the spectrum blocks, we do inverse FFT for each of them to get the real audio signal blocks and concatenate them all. Also, to do signalization, we add a chirp as the preamble of the whole signal and use match filter at the receiver. By OFDM, the baud can be really high, more than 3000 bits per second, so we still need a bit error correcting mechanism to deal with the burr. Here we use half-rate convolutional code with hardization, which be algorithm to decode.
Our results worked quite well with a higher PSNR than the baseline by 2 for most videos. We can see the effects of quantization motion vectors here, which were our most lossy parts in addition to downsampling. Because we had an increased baud rate, we could send more information, which allowed us to have a lower compression factor.
He's working on the compression part. Then I'm gonna do the reconstruct the video.